an odd presentation out in this session. This is the one talk that's not about solar. So don't ask me what would happen if it's not sunny. I was going to ask you that question. Scott Summers said that he's new to sanitation and is learning a lot from this conference. I'm the same way. Actually, everybody on our very large team is the same way. We had not worked on sanitation before we got the grant from the Gates Foundation. So our approach is quite different than most of what you're hearing on at this conference. And I'm definitely learning a lot by listening to all the different approaches, from technological to community-based to everything about business approaches as well. So a very long title. We're mostly chemical engineers with some mechanical engineers as well. So this is the unit operations approach is very much a chemical engineering approach. And we're trying to meet the design objectives that were set for us by the Gates Foundation, which we all know now, 5 cents per person per day, off-grid, very rapid disinfection within about 24 hours. And we were also trying to be careful to make sure that our process was going to be contextually appropriate. At least we tried to understand a little bit of what that context was about. And we had partners in Bangladesh who helped us meet with women from villages in Bangladesh, and they told us about what their preferences were, what their daily practices were, and so forth. And we tried to incorporate that as much as we could. So here's the overall process, and this is not done to scale. So we have four unit operations. So if you're a chemical engineer, that would be a very familiar term to you. There's a sand filter, a UV disinfection unit, a belt drying unit, and a smoldering unit. We think that we're going to use a source separation. Okay, so solid stream, there'd be a hole for solid waste. So fecal solids are now, some liquids from diarrhea, and possibly some solids as well. Actually, definitely some solids as well. And that stream would go into a sand filter, which will filter out the solids from that stream. And what leaves the sand filter to go into the UV disinfection unit would be just the liquid stream. And our design criteria is to remove solid particles that are larger than about 10 microns, which is what we need in order for the UV to be effective. What comes out of the UV disinfection unit is disinfectant water. And so you can imagine this solid contaminated liquid stream going through the filter. The top of the sand filter is going to be contaminated. So you'll have dirty sand, you'll have all the solids that are retained there. And that'll be skimmed off the top of the sand filter onto a belt, and also goes into the smoldering unit. So the solids from both the feces stream and the sand filter, the top of the sand filter will be processed by the smoldering unit. And so what comes out of the smoldering unit is sterilized sand, as well as any inorganics that comes from feces. And so the material balance, if I had a pointer, I could show you. The material balance would be the human waste comes down from the top. We get sterilized sand and ash out on the right-hand side. We get disinfectant water out on the left-hand side. And the sand has to be made up, and that's fed into the sand filter. So that's the material flow. The energy flow is just these two different arrows here, the black arrows here. The smoldering unit only requires the energy input to ignite it. So the amount of energy needed, we estimate it to be about the energy content of one person's fecal output in a single day. So it's not a large amount of energy. The UV disinfection unit, we made all our calculations assuming 15 watts. We didn't actually do any experiments with UV yet because UV is so well understood. 15 watts is way more than enough. 5 watts is probably going to be enough. Okay. So that's the only energy requirement. We had to do a number of things. My graduate students and research associates, for some reason, don't like playing with real feces all the time. And so we came up with a formulation for surrogate feces to match the caloric content of the literature values for human feces that we found. We also came up with a formulation for surrogate diarrhea to match the particle size of diarrhea. We actually could not find in the literature the particle size of diarrhea. So we made up simulated diarrhea using real feces, but diluting it, essentially soaking in water for some extended period of time. And we found a bimodal distribution of particle size, which makes sense to us, actually. And then we made up a formulation of surrogate diarrhea to match that particle size distribution. So to go through the 4 modules, so each 4 individually sounds really simple, and they are, but we did a lot of engineering analysis to try to understand how each of these units worked. For the drying experiments, for the drying belt, what we did was to measure the rate of drying as a function of time, so the drying kinetics. And from that, we matched it to a transient diffusion model to work out an effective diffusion coefficient for water diffusing through feces. And then using that effective diffusion coefficient, we can then predict the water content in the feces as a function of external conditions such as such as relative humidity and temperature, and also the geometry of the feces, the thickness of the feces in particular. And so with that kind of analysis, we're then able to, if you can look at the green curves on this graph, this is assuming 28 degrees Celsius and either 85% relative humidity or 50% relative humidity. You can look at, so the green graphs giving you the moisture content after 24 hours remaining in the feces as a function of the thickness of the feces. So if you flatten it to different thicknesses, the flatter it is, so the lower the thickness, the drier the feces is going to be after 24 hours. But you can tell that as you get thinner and thinner, beyond about 4 millimeters thick, it doesn't matter anymore. Because when you get thinner, when you get to that level of thickness, then at 24 hours it's already equilibrated with the ambient conditions. So making it thinner doesn't matter anymore. Whereas if you made it thinner, then the length of the bell that's needed for however number of users that you have on your scale, and the volume of feces that would be produced by that number of users would increase. So we like for the feces to be thick, so we can reduce the footprint of the drying unit, but thicker means it's going to get not quite as dry. But still looking at this, if we wanted to get to 50% moisture content at the end of 24 hours, when the ambient condition is 85% relative humidity, then it requires a thickness of about 6.2 millimeters. And that translates to a belt length of about 2 meters, which is quite a lot. It's quite long. But 85% relative humidity is a pretty high humidity condition. But we had a nice, clever little idea where we could use, what we found was that when we rolled feces between 2 rollers, between belts, by choosing the right materials for the belt, the feces actually was split between the top and bottom layers. So we effectively reduce the thickness of the belt we effectively reduce the thickness of the belt by a factor of 2, and therefore the footprint can be a lot smaller. Okay? So the belt length can be a lot shorter. So that's what that looks like with this feces splitting in 2. Moving on now to the smoldering module, which is the main module that we have for destroying the solid waste. Smoldering is just like combustion. Okay, so it's the same chemical reaction as any open flame, but the difference is that in an open flame, the reaction takes place in the gas phase. So it's a carbonaceous fuel reacting with oxygen to form CO2 and water. In smoldering, the reaction takes place at the surface of the solid fuel. So you get this glowing red fuel rather than an open flame. And most of you are probably familiar with having done a charcoal barbecue. So this is exactly the same as a charcoal barbecue, except the fuel is dry feces rather than charcoal. And so, and also you're probably also familiar from the charcoal, from having barbecued before, that as long as once you get the barbecue started, as long as you keep adding charcoal, you can add cold charcoal, but as long as you keep adding charcoal, that smoldering will continue to take place. So smoldering can be made to be self-sustaining. What's important is that you have this contact between oxygen and the fuel surface. So the permeability of the fuel bed is important. How you pack the charcoal is important. Okay? And so the key idea that we had, if you imagine if you put feces, try to pile feces into a container, it's just going to compress, and you're not going to have a lot of airflow. So the key idea that we came up with in trying to promote the airflow for smoldering of feces was to mix the feces with sand. The sand is not compressible, and therefore you'll get pathways for air to flow through the bed. And so this is what a typical smoldering experiment would look like. This is with surrogate feces mixed with sand. In the first graph, in the first photograph, all you have is it's initially heated using an electric heater. Then at some time, after it's been heated for a certain amount of time, airflow is started, and then you see the smoldering front moving upwards. The black part is the smoldered feces, okay? Until eventually you run out of fuel and then the reaction stops. Let me try to, how do I move this? Can you show me how to cook this? Sorry, I'm a Mac person. Okay. So, it's a video. How do I click on this? Oh, okay. Okay, thank you. So, so this is an infrared camera view of a smoldering reactor. It shows you how the smoldering front is moving upwards through that bed. It happens at a fairly constant velocity, depending on what the experimental variables are. And so, I won't show you all the data that we have. We have a lot of them. But what's important was to find the conditions when smoldering can be seen to be self-sustaining. So again, if you've done charcoal barbecues, you know that sometimes you can't get it going. You'll try to ignite it, but for one reason or another, you'll just stop. And it's not the easiest thing to start a charcoal barbecue. I mean, that's why gas barbecues are so popular now. But we found conditions when the self-sustaining smoldering can be seen. And you can play off on the various parameters that affect whether smoldering is going to be self-sustaining. Permeability is primarily has to do with whether the permeability of the bed is high or low. And permeability is enhanced if you have drier feces. If you have higher sand to feces ratio, because that promotes the porosity of the bed, and it's also enhanced by having large sand particles. But you can balance these various factors to find the optimal conditions. Okay. And what we find is that you get a peak temperature of 600 to 800 degrees within this bed. So the organic matter in the feces is completely destroyed. The only thing that remains is sterile sand and the inorganics that are in feces. So other things that we did some work with, not a lot yet, is to try to capture the smoke and odor that comes out of the smolder, and also working on ways to we're working on ignition protocols without using an electrical heater. So this could be something like local rice husks or cow dung or something like that. And one important thing to point out is that the rate at which the feces is destroyed can be controlled by the airflow rate. So our thought is to run the smoldering reactor using just natural convection, but having a valve to valve down the airflow rate, and therefore control the rate at which the smoldering can take place. Just a sample calculation. So we try to relate the experiments to what the design of the reactor is going to look like. So at the lowest consumption rate shown in this graph of 0.2 kilograms per milliliter per square meter, for a 10-person scale, it works out to a smoldering diameter of 11.5 centimeters. So it's not big, it's about that size. Okay. Now, moving on to the third unit that we have in our unit operations process, it's a sand filter. And what we designed for was two things we were worried about. One, it has to filter each liquid bolus quickly. So liquid with solid contaminant bolus. Each one has to be filtered quickly. It cannot clog. And so for this design criteria, the larger the particle size of the sand, the easier it would be to meet. But our second design criteria for the sand filter is that it has to remove particles that are larger than about 10 microns, because our subsequent process is a UV disinfection unit. And that second design criteria is easier to satisfy if we have smaller sand particles. So the two things are opposing. But we worked out conditions when we could satisfy both of them. And so this is what the optimal conditions would give us. Using pretty well a worst case situation, using a very high solids content, assuming half of the solids in the diarrhea bolus is washed into the sand filter with urine and with personal wash water that will be used in the same use. So that's what the liquid will look like, in the very brown liquid with solid suspension in it. Going through our filter, we end up with essentially a clear liquid, still brown, but the solids content is very, very low. And that then goes to a UV reactor. So that liquid that comes out has a UV transmittance of 2%. Okay, so that's something that we need to know in order to design the UV reactor properly. And the sand is fed from the bottom using an auger conveyor and then skimmed off the top, as I described earlier. And so an operation of this looks something like this. Okay, this is a sand extrusion video, but I can't get it to work. So essentially, let me just describe this. So bolus is deposited into the bowl on top. The liquid filters out, and by the sand is extruded upwards, so you see a bit of that sand extruded into the bowl on top, and a paddle is used to skim that sand off out of the bowl and onto another belt. And then the filter is ready for the next use. The final unit is a UV disinfection unit. Okay, so the most important thing to know about UV disinfection is that the fluid element, whatever liquid that you're trying to disinfect, has to be subjected to a minimum UV dose. And that dose, based on what people in the UV industry tell us, is 24 millijoules per centimeter squared. And that dose is a combination of the intensity of the UV that each fluid element experiences, multiplied or integrated over the time in which that fluid element stays in the reactor. So is the integral of the UV intensity as a function of time, and therefore we also need to know whether we need to know two things. One, what is the UV intensity distribution within a reactor, and two, what is the velocity profile in that reactor. So it's a typical, because the UV transmittance is quite low, it's only 2%, we had to design a very thin film reactor. And in that thin film with very low flow rates, we expect the flow to be laminar, and you get your typical semi-parabolic velocity profile. And we put the UV lamp on top, above the liquid film, so that the sleeves of the lamp would not be fouled. And so we modeled the UV lamp as a number of point sources, and each point source radiates intensity in all different directions. We can sum up all those, all the intensity from the multiple sources to figure out what the intensity is at every point in that thin film reactor for varying thicknesses. And that intensity, again, integrated. So if you think of a fluid element flowing up on top, at the top layer, it's going to see a certain intensity as it goes through every point of that reactor. And a fluid element flowing below that surface is going to see a lower intensity, but it'll have a longer residence time within that reactor. And what we can then work out what the UV dose is as a function of the depth in that film for given average velocities, and also for given film thicknesses in a reactor. And what we then did was to just take all that information and summarize it in terms of a design graph. So given the UV transmittance of 1%, 2%, 3%, or 5%, each of these curves gives us the combination of average velocity and film thickness, below which we would get enough dosage to disinfect everything that we're supposed to disinfect. So everything below these curves is a reasonable operating range, is an effective operating range. So I won't go through these design calculations, but essentially, if the average velocity is 0.5 centimeter per second, then a film thickness of 0.65 centimeters or less will be enough for us to get enough UV disinfection. And this is very easy to achieve with 15 watts per UV lamp. You can go 4 or 5 watts, and we still have lots of room to work with. So what we did in phase 1 was essentially a proof of concept of each of the 4 modules. And we showed that the feces can be dried to the moisture level that we need for smoldering within 24 hours with a reasonable belt length. We showed that a sustainable smoldering can work over a wide range of variables, and that we could control that smoldering rate. We also showed that the sand filter can effectively remove particles that are larger than 10 microns, which would then give us the feed that we need for effective UV disinfection. And in meeting the RTTC criteria, solids are disinfected within 24 hours. Liquids are disinfected very, very quickly. Just essentially the filtration time within a sand filter. The energy budget is quite low, and the way we did a cost estimate was actually to our Bangladesh partner went and sourced every component in our prototype locally, and we figured out the cost for that. That's just the retail cost. Any reasonable discount for volume production, and we can easily meet the 5 cents per person per day target. We tried to understand the users, as I said. We also tried to understand what the local capacity was for maintenance and operation. And so there's some machinery capabilities in the Bangladesh villages, near the Bangladesh villages that we worked in. And the picture on the right is actually a smoldering unit. It's used to smolder rice husks for heating up water, and the pipes around that, on top of that, it takes steam and then pipes it into a process for boiling water. So sorry, for boiling rice. Boiled rice is a product that's made in that part of Bangladesh. This is a bit of a scary picture. So one other part of trying to make this locally appropriate was that even though we wanted to make sure that this is very simple to operate, it doesn't mean that the design of it is necessarily simple. So one of my research associates said, no, simplicity ain't simple, which I think is true. And we did many experiments. We did lots of calculations and lots of engineering design thinking. But this is the most dramatic picture of what I mean. So with the smoldering, as I said before, smoldering is the same as an open flame reaction, combustion reaction. So there are conditions when you can push the reaction to take place in the gas phase. But we had to make sure that it stays as a smoldering reaction rather than an open flame combustion reaction. We actually pushed it to the point where we can see open flame, and our operating condition is very far away from it. And so I wouldn't want to use that toilet. So I just wanted to make the point that it is important to think through a lot of these things and design for safety as well as easy operation. Okay. Made a three-hole squat toilet, and that's what we did. But going forward, what we want to do, one of the criticisms that we have of ourselves and of this process is that even though each module seems to be quite simple, there are actually a lot of moving parts, and to put all four together is a little bit complicated to operate. And so moving forward, so all we did in phase one, all we had time to do was to prove that each module is feasible. And going forward, we're going to integrate them, and what I always say is we're going to simplify. And we've already made progress since we showed this prototype in Seattle in August. And some of those modules that I showed you are not going to survive, but I'm not ready to tell you what our plans are yet. We are also going to try to make use of the heat that we can get from smoldering, which we didn't try to do in phase one yet. We can also try to capture clean water from this process. There are lots of user touch points in the process that I described. Again, those will be minimized and simplified as we go forward. Containing odor, which everybody's trying to do, and also containing this